You join a 50-person Zoom call. Everyone's video loads instantly. Audio is crystal clear. But here's what's actually happening under the hood. Without a central media server, your laptop would need 49 simultaneous incoming video streams. At 1080p, each stream is 3.8 Mbps. That's 186 Mbps of downstream bandwidth, just for you. Consumer internet tops out around 100 Mbps. The math is impossible. Yet Zoom went from 10 mem daily participants in January 2020 to 300 memons in April 2020. That's a 30x surge in 90 days. This is how they built the architecture that survived it. These numbers put real-time video in a different category entirely. A missed HTTP packet retries silently. A missed audio packet is perceptible. Every 20 millisecond frame matters. A 50-person call generates 2,450 peer-to-peer connections in full mesh topology. That's ON² connections scaling with every new participant. At peak COVID load in April 2020, Zoom was handling 300 mem daily participants. Their infrastructure grew from 17 co-location regions to provisioning 2,000 additional MMR instances on AWS in under 3 weeks. No system designed for HTTP traffic survives this. Real-time media demands an entirely different playbook. Think of a full mesh network like every person in a room shouting directly at every other person simultaneously. At 5 people it works. At 50 it's chaos and impossible bandwidth. The alternative before SFUs was the MCU, a multi-point control unit. It decodes every stream, mixes them into one composite video, then re-encodes and sends one stream per participant. Clean bandwidth, brutal CPU. A 100-person MCU meeting adds 10 to 50 milliseconds of encoding latency alone. The SFU is the third path. It receives all streams, it forwards selectively, it never decodes a single packet. That distinction, routing versus processing, is everything. Every Zoom publisher sends 3 simultaneous video streams. High layer 1080p at 3.8 Mbps, medium layer 720p at 1.5 Mb, low layer 360p at just 400 pb. The SFU doesn't pick one for everyone. It picks a different layer per subscriber based on their available downlink bandwidth, their display size, and whether they're the active speaker. The MMR checks RTCP receiver reports every 200 milliseconds. Packet loss above 5% triggers an immediate layer downgrade. Loss below 1% for 2 consecutive seconds triggers an upgrade. Layer switches complete within 1 keyframe, typically 300 milliseconds to 2 seconds. The viewer never sees an artifact. That's the contract. Here's the core logic running inside Zoom's MMR every 200 milliseconds. For each subscriber, it reads the latest RTCP feedback, packet loss ratio, jitter, and round-trip time. If loss exceeds 5%, it immediately steps down 1 layer. If loss stays below 1% for 2 consecutive cycles, it steps up. Active speakers are pinned to the highest available layer, regardless of their subscriber's bandwidth signal. This is production-grade bandwidth adaptation. Discord runs nearly identical logic on their video infrastructure. The elegance is in the simplicity. 1 metric, 3 layers, 1 decision every 200 milliseconds. That loop runs millions of times per second across Zoom's fleet. Watch what happens the moment you click join. Your client fires an HTTPS request to Zoom.us signaling servers. The server returns your assigned MMR IP address plus turn credentials. Your client probes stun to discover its public IP. It tries direct UDP to the MMR. This works for 80% of networks. If blocked, it falls back to turn relay, adding 10 to 30 milliseconds. DTLS SRTP establishes the encrypted media channel. For E2E meetings, an additional key exchange fires through the KMS here. Your client signals supported codecs, H.64 primary, VP8 fallback, Opus audio. The MMR responds with encoding targets. Total time from click to live video, under 2 seconds. Standard WebRTC is a browser standard. Zoom's native desktop clients don't use it. They built a custom UDP transport on top of RTP, tuned for their infrastructure. For audio, they use forward error correction. Lost packets are reconstructed from redundant data. No retransmit delay. For video, they use selective NAC retransmission. Only critical packets get resent. Congestion control mirrors Google's REMB algorithm but is tuned specifically for Zoom's global MMR topology. When corporate firewalls block UDP entirely, Zoom falls back to TCP port 443, disguising media as HTTPS traffic. That fallback adds 30 milliseconds of latency but maintains the call. Browser clients on the Zoom web app do use standard WebRTC. Zoom operates 17 co-location data center regions globally. They're not purely cloud, it's a hybrid of Colo plus AWS, Azure, and Oracle Cloud. When you join, DNS resolves you to the nearest signaling cluster. The signaling server pings candidate MMRs and picks the one with lowest latency to you and acceptable current load. Media flows client to your regional MMR, then MMR to MMR over dedicated backbone, not the public internet. Cross-region latency budget is under 80 milliseconds. Total end-to-end audio target is under 150 milliseconds. During the April 2020 spike, Zoom provisioned 2,000 additional MMR instances on AWS EC2 C5N9X large, 36 vCPUs, 96 GB RAM, 50 GB piece of network in 3 weeks. Think of NAT Traversal like getting mail delivered to an apartment with no street address. Your router hides your real internal IP. The outside world can't reach you directly. Stun lets your client discover its public IP and port. That works for roughly 80% of home networks and simple NATs. But enterprise networks often use symmetric NAT. Every new destination gets a different mapped port. Stun fails. ICE then falls back to turn, a relay server that accepts your packets and forwards them onward. Turn adds 10 to 30 milliseconds of latency. Zoom runs turn servers in every one of its 17 data center regions. No region lacks a turn fallback. That's why your corporate Zoom call still works behind the strictest firewall. In April 2020, Zoom faced a public controversy. They claimed end-to-end encryption. Security researchers proved Zoom servers could decrypt the media. Zoom launched True E2EE in October 2020. Here's the difference. Default transport encryption uses AES 256 GCM between client and Zoom servers. Zoom decrypts, inspects, re-encrypts. Their servers see your video. True E2EE generates the session key on the meeting host's device. That key encrypts with each participant's public key. The KMS distributes the encrypted keys, but never sees the plaintext key. Zoom's MMR forwards encrypted packets it cannot read. The trade-off is explicit. E2EE breaks cloud recording, phone dial-in, and live streaming. Keys rotate every 30 minutes in long sessions. Now here's where it gets interesting. Zoom isn't the only company solving this. Google Meet uses standard WebRTC, but replaced DTLS SRTP transport with WebRTC over QUIC. QUIC gives stream-level multiplexing. One drop packet doesn't block all other streams. No head-of-line blocking. Their SFU connects directly to Google's Jupyter Backbone network. Microsoft Teams uses SFU architecture with a twist. They introduced MeshFU, multiple SFU nodes interconnected for enterprise meetings exceeding 1,000 participants. Discord handles voice differently. They use WebRTC for small calls but built custom DAVE protocol, Discord's AV-E2EE, launched in 2024 for end-to-end encrypted voice in servers. Same core problem, 4 different implementations. The SFU pattern wins across all of them. Active speaker detection is the intelligence layer above the SFU. Every 300 milliseconds, the MMR scores each participant's audio energy level. The highest energy score wins the active speaker slot. That participant's stream gets promoted to the high Simulcast layer for all subscribers. But here's a critical production detail. You need hysteresis. Without a minimum hold time, speakers switching every 300 milliseconds causes constant layer thrashing. Keyframes fire continuously, bandwidth spikes, video stutters. Zoom holds the active speaker designation for at least 600 milliseconds before switching. That single engineering decision prevents a catastrophic feedback loop at scale. This same pattern appears in WebRTC conference systems from Jitsi to Amazon Chime. Real-time video at scale is a fundamentally different problem than building HTTP APIs. The SFU pattern, route without decoding, is the architecture that makes 300 meme daily participants possible. Simulcast with per-subscriber layer selection solves the bandwidth heterogeneity problem. One participant on 4G gets 360p, another on fiber gets 1080p. Same meeting, same SFU, different layers. NAT traversal with stun, turn, and ICE is non-negotiable for enterprise deployments. 20% of calls hit turn. Zoom builds turn into every region. Custom transport beats generic standards at scale. Zoom's proprietary UDP stack outperforms WebRTC for native clients. And E2EE is an architectural choice, not just a checkbox. It fundamentally changes what your servers can see. Zoom's entire 300M participant architecture runs on one insight: route packets, never process them. That's the SFU. Next video, how Discord handles 19M and concurrent voice users with their custom media infrastructure, and why they eventually abandoned WebRTC for parts of it. Subscribe so you don't miss it.